Welcome to 6.2, where we're going to be talking about classifying the elements. In 6.1, we dealt with introducing you to the idea of the periodic table, its historical development, and what it is. And again, it's a table of repeating properties. Every time you start a new row, which is, of course, when you're going from left to right across the periodic table, each new row or new period starts the properties over. And so what ends up happening is the elements that are in columns, which we call groups or families, all have similar properties. Okay? And so many of these actually have special names. So we're going to be going through and just naming the families or the groups as you go down the periodic table. In group 1, and by the way, we do number the columns 1 through 18. That is a relatively new development. In the past, they used numbering systems using numbers and letters, actually Roman numerals and letters, but they've relatively recently changed that over to 1 through 18. So in column number 1, or group number 1, we're going to skip hydrogen, but going from lithium on down to francium, we call this group of elements the alkali metals. When you put them into water, they do form basic or alkaline solutions. All right. In group number 2, changing colors here. Group number 2, from beryllium on down to radium. And generally, we're usually speaking of magnesium, calcium, strontium, and barium, but beryllium and radium do fall in this column as well. We call these the alkaline earth metals. Now, the alkaline earth metals also will form basic solutions. From what I understand, the term earth is an old term that people use to describe something that often was connected with oxygens. So you would often find calcium, magnesium, strontium, etc. in some type of oxide form. All right, don't quote me on that, but that's generally what I've understood that to be. In this middle group, the D block, for those who did Chapter 5. You know that this middle section is called the D block. These are called the transition metals. They have a wide variety of properties. It's not that they all share identical properties or incredibly similar properties, but they do vary. And for example, one of the properties that the transition metals tend to have is that they form several different oxidation states. For example, iron, element 26, can be a +2 or a +3. Copper will be a +1 or a +2. Manganese will be anywhere from +2 all the way up to a +7. Chromium can be +3s and +6s. So there's a lot of different oxidation states that these transition metals will occupy, or will have. All right, moving on over. Actually, I'm going to scroll this down just a little bit. We're talking about the transition metals. The F block, I'm going to do this in a different shade of green. We'll throw them lime green. How's that? Let's see if that shows up. The F block here, down below the periodic table. Of course, the F block actually fits right in between the alkali metals and the transition metals. That's actually where it would fall. And so, because these transition metals of sort fit inside of this periodic table, we call them the inner transition metals. Oops. Transition metals. All right. They also have a wide variety of properties. Now, going all the way over to the opposite side, column number 18, helium on down to radon. These are called the noble gases. Now, they used to be called the inert gases, meaning that they did not react with other elements. But as recently as, say, 40 to 50 years ago, they have been able to force these elements, particularly xenon, to form certain types of compounds. So we no longer call them inert because we can actually force them to react. But most of the time, they're not going to be doing anything. All right, moving over one column to the left from that. Let's change up colors. Let's go orange with this one. Starting with fluorine on down, typically we don't include astatine which is in the bottom here. So maybe I'll block that one off. Astatine, this last element here, that element is in such small quantities. I believe it's only about a teaspoon of this stuff is in existence on Earth at any given point. It's very unstable and quickly decays into other elements. So generally speaking, when we're talking about group number 17, which we do call the halogens, we're typically only talking about fluorine, chlorine, bromine, and iodine. All right. Now the rest of these elements, I'll just kind of shade them in yellow. The rest of these elements here are generally talked about in terms of their group numbers or the first element in the group. For example, this first group number 13, we might call that the boron group. 14 we might call the carbon group, the nitrogen group, and the oxygen group. We don't have any special names for them. All right, so it's important to know what these families are because they do share similar properties, and oftentimes we'll be talking about, in terms of a chemical reaction, the fact that you could take any alkali metal and do this with it, or take a halogen and do this with it. So you should be able to recognize the various families. All right, scrolling down here, we're going to reiterate the names of the, just so that you can remember them, and we'll get them in another list here. So once again, switching up colors, try to color code it. Group number 1, alkali metals. Group number 2, switching over to the blue, is going to be the alkaline earth metals. Group 3 through 11, we did in a green color. Those are the transition metals. Group number 17, we did in orange. Those were the halogens. By the way, the term halogens means salt-loving. The halogens tend to form salts. Sodium chloride is table salt. And that last group over there we did in violet was the noble gases. And if we scroll down just a little bit, the F block we did in this lime green color, and those are called the inner transition metals. And finally, groups 13 through 16 again are just usually referred to by group number or the first element in the group. The last thing that we want to tackle in this section is the fact that these families are organized by electron configurations. Now, if you didn't cover Chapter 5, this might not make sense to you, and so feel free to just stop the podcast. But for everybody else, as it turns out, the electron configurations give these elements their properties. So when we're talking about the alkali metals, the reason why they behave together is because they're all ending in S1 configurations, 2S1, 3S1, 4S1, etc. When we're talking about the alkaline earth metals, the reason why these alkaline earth metals behave similarly is because they have 2 electrons in the s orbital, and that's the last 2 electrons that were placed in there. The transition metals are all filling the d block. The inner transition metals are all filling the F block. All right? The halogens, which tend not to react, have a completely filled outer shell. Whether it's the P6 or in the case of helium being an S2, but it only has the s orbital and it is completely filled. The reason why the noble gases tend not to react is because they have a completely filled and very, very stable electron configuration. And then, of course, the halogens are short 1 electron from the noble gases. They have a P5 configuration. But once again, it's the electron configurations that give these things their similar properties. And as it turns out, the periodic table is based on 2 things: increasing numbers of protons and repeating electron configurations. That concludes 6.2.